what we're going to do is we're going to go over some of the homework from 8-2, which is area between curves. And these are the problems that Green class suggested that they wanted worked. So the first one I'm going to do is y equals sine x and y equals 1 minus x. So we're going to draw the curves. And 1 minus x squared I'm going to draw first. So that's 1, and that has intercepts at 1 and -1. And that's just a parabola that opens down. And I know it's awkwardly drawn, but, you know, it's by hand. Handcrafted with love. All right. Y equals sine x. Well, sine is 0 at 0. And it's 1 at pi over 2, which pi over 2 is 1.57. So I'm just going to put pi over 2 over here. So it's going to be at 1 here. There we go. So it's going to go up like this. And then it's -1 at negative pi over 2. So we'll put a -1 down here. And so this curve, the sine curve, is doing this. Well, not quite that. Let me do it right here. Trying to be perfectionist on camera is not always a good plan. Anyway, so we're trying to find the area between these two curves, which turns out to be this area right here, which is easy enough to set up from an integral standpoint, from the integrand standpoint, because what we would do is we would say that the area is equal to the integral, and I'm going to call this point A and this point B. From A to B of the upper minus the lower. The upper one is 1 minus x squared minus the lower, which is sine x dx. Well, the tricky part here is that we have to use a calculator to find the points of intersection of that curve, and the sine x and the other. Okay, so in order to find those points of intersection, we're going to need our calculator. So I'm going to get out our calculator, or my calculator. And here it is. So I'm going to go to y equals and put in my curves. And I'm going to put into y1, 1 minus x to the second, minus, and y2. Oops, I'm sorry, go back. Escape. That's 1 minus x to the second, and y2 we're going to go second sine of x. All right, there we go. And I'm going to go to graph. But before I go to graph, I'm going to do a zoom trig, because I've got a trig function, and I'd like to see a nice trig zoom window. There it is. There's our function. And of course, there is our area of what we spoke here. All right, so how do we find the point of intersection? Well, we do some math, and we're going to do intersection. And I'm going to go over here with my arrow and say that's the first curve, that's the second curve. The lower bound, make sure I'm on the left side. Now we're going to go to the right side for the upper bound. And there we go. So the point of intersection here is, let's write this down. A is going to be negative 1.40962. And the B is negative 0.98. Negative 0.98704. That's the y that goes with it. Now, before we go any further, I want you to notice that we've got the intersection point stored in xc and yc. So I'm going to go home to the home screen. I'm going to type in x alpha c, and I'm going to tell the calculator to store it with using the store key, which is the stow here, stow, and alpha a. Okay, and so now I have the x value stored in alpha a. And I'm going to store now I'm going to go and go back to the graph, and I'm going to find this intersection point and store the xc into alpha b. So we can have a rounded answer, which would be very good. So we're going to go do some math, and we're going to do some intersection, and First curve, yes. Second curve, lower bound, and on the right side of the intersection point, and the calculator is going to tell us the intersection point for B is 0.6367327. I worked this before, so I know the exact answer. So this is 0.59455715. All right, but we're going to use our calculator here and store that answer in B. So we're going to go to the home screen. Notice again that this is XC, so we've got to remember that. We're going to go home, and instead of storing XC in A, we're going to store XC in B. So alpha B, there it is. And now we're going to integrate this. Now I stuck this curve when I worked this problem. I stuck that curve in y1, and I stuck this curve here into y2. Okay, so we can use our calculator to our best advantage by clearing this out and going F3 integrate. And I want to take the upper curve, which was y1 of x, minus the lower curve, which is y2 of x, comma, with respect to x, comma, and I'm going to go from alpha A, comma, to alpha B because I have those values stored. And that'll give me the exact answer, or the non-rounded answer, or the final answer will be rounded, but not any in between steps. So this will be 1.670 units squared is the area. Okay, so the key to working these problems is that you should store your intersection points, and it's really easy to do. And so that's how you set up that one. And Death 7 is definitely a calculator question. All right, moving along to the next question, which was question number 9. Now, number 9 is a non-calculator question, and we have to set up two integrals here because I have one function that's the upper, and this is the lower function for the whole thing, but I have two different upper functions. So I have to bust up the integral in the middle here. And so I can say that the area is equal to the integral from 0 to 1 of this upper function, which is x, minus the lower function here, which is x squared over 4 dx, plus the integral from, now I'm going to go from 1 to 2, and the upper function in this case is 1, minus the lower function, which is x squared over 4 dx. And we have to integrate each one of these separately. So this is going to be x squared over 2 minus x cubed over 12, evaluated between 0 and 1, plus the integral of this one will be x minus x cubed over 12, evaluated between 1 and 2. And then let's put using the fundamental theorem of calculus part 2, let's see what we get. When I plug 1 in here, I get 1/2 minus 1/12, minus 0 wipes it out, so minus 0, plus when I plug 2 in here, I get 2 minus 8/12, minus when I plug 1 in, we're going to get 1 minus 1/12. And when we simplify all of this, we get 6/12 minus 1/12, plus this is 24/12 minus 8/12, and this is minus 12 over 12 minus 1 over 12. So this is going to be a negative 11/12. And this means when we add it all up, we're going to get, well, that's going to be 6 minus 1 is 5, and 24 minus 8 is 16, so that's going to be 16 plus 5 is 21. 21 minus 11 is 10/12, which is equal to 5/6 units squared. And the key to this problem is that we have two different upper functions, so we have to integrate using two different integrals, going to 1 and then from 1 to 2. Third question you had was, I think, the hardest one of the homework, and I have been known to put this one on a test. Yes, I have. And this 33, I'm going to be drawing, this looks like it's in terms of x in terms of y, which means this is going to be similar to the inverse tangent function, but not really, because it's squared. And if it's squared, that means this function that it's always positive. And what happens as y gets very, very large? Well, tangent squared is going to approach, when y is pi over 2, the tangent is undefined. So I believe it's going to look like this, because that's kind of like the tangent graph. I mean, the inverse tangent graph, but it's always positive. And so it's an even function. So we're going to do this. Now, I wouldn't necessarily expect that you know what that looks like. Let's have, using Desmos here, x equals tangent, parentheses, tangent of y. Oops, interesting. Hold on a minute. My sketch is wrong. So let's try it again. See, even Mrs. Muller can be a little bit imperfect. The x's are always positive. I got it backwards. I thought the y's were always positive. Now, what do I mean by that? I was thinking of it as y equals tangent squared x, which means the y's are always positive. I mean, the x, yeah, in this case, it's the x's that are always positive in this case. So it's going to approach this function. Let's see if it approaches y equals divided by 2. It looks like it does, which is nice. And so that part I had right. All right, but still, when I plug in 0 for y, I'm going to get 0. And it looks as though this function is going to do this. And it's going to almost act parabolic, which I find fascinating. Okay, so when the y's are, when the x's are negative, it's going to be this function. So this function is this one over here. So negative tan squared y, and this one is x equals tan squared y. Okay, and we want to find the area between these two curves, between negative pi over 4 and pi over 4, as I receive the question here. And if I were to do that, it looks as though I'm going to be finding this area in here. All right. So if I'm finding that area in here, I have to integrate with respect to y. So this right here is going to be my little slice dy, because I'm going to use symmetry as my friend here. And I'm going to only find the area. I'm only going to find the area of this here, and then I'm going to multiply it by 4, because I think that would be easier, right? If I found this area and then multiplied it by 4. So y is going to go from 0 to pi over 4. And what is this distance? Well, this distance is x equals tan squared y. Okay, so let's write that one down. The area is going to be equal to, using symmetry, we should always tell the grader what we're doing. The area is going to be 4 times the integral from 0 to pi over 4 of tan squared y dy. Well, tan squared is one of those that we need to know how to integrate. And that's going to be 4 times the integral from 0 to pi over 4 of, we have to use the identity, secant squared x minus 1, because we know, secant squared y. Secant squared y minus 1, because we know whose derivatives these are. So when we find the antiderivative, it's a whole lot easier. So this is going to equal 4 times secant squared y is tangent y's derivative minus y, and we're going to evaluate it between 0 and pi over 4. So we get 4 times the tangent of pi over 4. Well, the tangent of pi over 4, as everybody knows, is 1 minus, well, we're just going to plug in pi over 4 here and then subtract 4 times, well, I'm going to plug 0 in here. The tangent of 0 is 0 minus 0, so we get a big goose egg there. So this is going to equal 4 times 1 minus pi over 4, which if you distribute the 4 is going to be 4 minus pi units squared is the answer. Sorry about the hiccup there on the graph. Just a major malfunction, but we straightened it out. All right, next one. Now I'm going to make this one a little bit bigger. Shows triangle AOC inscribed in the region cut from the parabola y equals x squared and the line y equals a squared. Find the limit of the ratio of the area of the triangle to the area of the parabolic region as a approaches 0. All right, well, let's see what happens. Well, I need to have the area of the triangle. Well, the area of the triangle we don't really have to use calculus for. So let's write that down. Area of the triangle. That's going to be A equals 1/2 the base, which I'm going to call this the base, and that's going from negative A to A, so that would be 2A, times the height, which is, this height here is A squared. It's A squared, and the 2's cancel, and so I get A cubed is the area of the triangle. All right, and now we're going to find the area of the region, the parabolic region. Well, that's the area between the line y equals a squared and the parabola. So our upper function is going to be y equals a squared, and the lower function is going to be y equals x squared. And I'm going to use symmetry again because, you know, x squared is pretty symmetric. Using symmetry, we can say the area is equal to 2 times the integral from 0 to a of the upper function, which is a squared, minus the lower function, which is x squared, dx. All right, so let's integrate that. We get 2 times, well, that's a squared is just a constant, so that's going to become a squared x minus x cubed over 3, evaluated between 0 and a. And so let's plug in a. We get 2 times a cubed minus a cubed over 3, which is equal to, well, the inside here is equal to 2a cubed over 3 times 2, which is 4/3 a cubed when it's all said and done. And now they want us to find the limit as a goes to 0 of the ratio of the triangle's area, which is a cubed, over 4/3 a cubed. Well, what happens algebraically here, we could use L'Hopital's rule, but we don't really have to here because we can cancel these out. So we cancel these out, and I get 1 over 4/3, which is 3/4. So that's the ratio as a goes to 0. All right, that was kind of tough just because of the all the letters, I think, but not impossible. All right, let's do the very last one. This one is find the area of the propeller-shaped region enclosed by y equals 2x over x squared plus 1 and y equals x cubed. All right, so y equals x cubed is easy enough to draw. And it's one of our toolkit functions that does this. That's easy enough to draw. Y equals x cubed. This function here is a rational function, but it has no real zeros And its horizontal asymptote is going to be y equals 0 because the degree of the numerator is smaller than the degree of the denominator. So I can put my horizontal asymptote here. And when x is 0, my y is 0. So it passes through the same origin point. And then when x is 1, we get 2 over 2. So that's 1. And since it said propeller region, I'm suspecting that it's going to look like this, because then that looks like a propeller, and then this is going to come back down and, approach the axis as x goes to infinity. So these are the propeller regions that they are talking about. And once again, I'm going to use symmetry. So I can say, using symmetry, I can say the area is 2 times the integral. I should make that my E nicer looking there. From, this is 1, 0 to 1, of the upper function, which appears to be the 2x over x squared plus 1 minus x cubed. Well, this x cubed is really easy to integrate, but this one is not so much. So let's split this up. We're going to go from 0 to 1 of 2x over x squared plus 1 dx. And then we can do this one. This one's going to be 2x to the 4th over 4 evaluated between 0 and 1, because we can integrate this one pretty quickly in our head. This one is going to take some u substitution. So we're going to let u equal x squared plus 1, du equals 2x dx, which I happen to have in here the 2x dx, which is really nice. And so then my integral becomes 2 times the integral of 1 over u du, but that's the natural log. That's the natural log function. And so we can say 2 natural log of the absolute value of u. But what is u? We said u was x squared plus 1. So we can say this is 2 natural log of the absolute value of x squared plus 1 minus, I'm going to reduce this, x to the 4th over 2. All this evaluated between 0 and 1. So let's plug in 1. We get 2 natural log of 2 minus 1/2. And then what happens when we plug in 0? We get natural log of 1, which is 0, minus 0. So we get another seg. So our answer is going to be 2 natural log of 2 minus 1/2. Now, that's unit squared. I noticed that in the book, they also give us an equivalent answer of the natural log of 4 minus 1/2 unit squared. And that's equivalent because I could take this 2 and bring it up and square the 2, and we would have the same answer as in the book. So either of these would be very acceptable answers. All right. So those are the questions you had on the homework. I hope this helped.